to start again. So we are we're in chapter 3, Ramsey numbers of sparse graphs. So we saw in the first section that in general for an n-vertex graph G we can only get an exponential upper bound on the Ramsey number in terms of n, and in fact we had exponential lower bounds as well. But now the question is, what if I take some much simpler graph, say a path or a tree? Can I get better bounds? And usually we aim for even linear bounds. So by sparse here, I'm being deliberately vague. We'll have various ways to formalize what sparse means, but I think we can all agree that maybe a path or a tree is a sparse graph, so it has like a small edge density, and a cycle is a sparse graph, and a complete graph is not a sparse graph. Okay, so on these problems, were there any ideas for constructions? I'll let you think about it for a bit then.
For the last one, can we take the graph on 2t minus 5 vertices, and then like do a Euler tour and then color the edges automatically?
Nice, yeah, that's very nice. So actually, for this one, 2t minus 5, this is, you've checked that the parity is always okay, so that you can get exactly 2t minus 5?
Yeah, one
okay.
should have like t minus 1 boost, t minus 2 boost.
Yeah, I mean, it doesn't really matter, it's minus 6 or something, but because the thing was Euler tours, or in general, so this is actually the general strategy is to for the red color to be t minus 2 regular, because you don't have vertex of degree t minus 1, and for the blue color to also be t minus 2 regular. And now your example with the Euler tours gives you a specific t minus 2 regular graph for the red. Yeah. So, and this Exactly, the Eulerian tour of the complete graph, it exists only if the degree is even, so that's why I wasn't sure. But yeah, and it's the same thing for regular graphs. These regular graphs, they exist when t minus 2 is even, or when the number of vertices is even, and then one has to check that maybe all cases are covered. I'm not sure, but it's roughly that bound. Okay, nice. Any ideas for the other two? So just a hint for this one, you're aiming for a bound of the type t times s. So certainly say ts over 2 would work, but something of that type. And for this one, we're not looking anything fancy because I think we don't know how to find anything better than 3t over 2. And as always, like there might be a -1 there. So yeah, I think even an upper bound is of that type here. We're not looking for anything fancy. We're just looking for something that's better than the trivial t.
We can take like path of size t minus 1 and then half of vertices which are not connected. That should be fine.
Okay, so for this one, okay, you need to somehow, okay, so you take a path on t minus 1 vertices, say, and then some other half of the vertices, but you need to somehow cover all the other edges. So, I mean cover as in color all the other edges. So yeah. The question is, how am I going to color all the other edges here and all the edges between those two? Mm-hmm.
And
yeah, I'm doing red and blue now, but yeah. You can also think in terms of cliques and independent sets, and this will be my blue, let's say. So then here everything is green. Okay, great. And now there isn't a red path because it's too few vertices in here. And there isn't a blue path because
we'll have to repeat the vertex on the right side if there is a path of
yeah. So it uses at most t over 2 vertices. The blue path would use at most t over 2 vertices on the right hand side, and because each vertex on the left-hand side costs you at most at least one vertex on the right-hand side, then you can also use at most t over 2 on the right. So altogether you don't get such a clique. Or again, sometimes I need a -1 here. I don't worry about things like that. Okay, and for the top one, so these are s minus 1, or maybe t minus 1. Let's see which one of those it is. It might actually be irrelevant. Wait a minute. We might have to swap these colors, we'll see. So this one, no, it could contain a longer path in green, so I need to swap colors, sorry. So this one is, yeah, you're right, t minus 1 is in green. So So the cliques are green. No, sorry, I changed the order of my, so the cliques are red because we're avoiding a red path, that's fine. And everything between is green. So basically we don't have a path because each path would have to, red path because it would have to fit in here, and we don't have a clique because each clique would have to use at most one vertex out of these S minus 1 cliques. Each green clique would have to use at most one vertex from each of these cliques and groups. Okay, so for the top one, we got a lower bound of t minus 1 times s minus 1, and we're going to show that actually that is sharp, and that is sharp actually for every tree, not just for a path. Because notice that inside red, you cannot fit any tree, or actually you cannot fit any connected graph. So this is actually a lower bound for all connected graphs versus Ks. So that's a classical theorem of Chvátal from 77. For a little t vertex tree t, we have that the Ramsey number of t versus Ks is exactly s minus 1, t minus 1 plus 1. So proof, so the lower bound is, as we said, so red is a collection of t minus 1 vertex disjoint Ks minus 1 copies, and the green is a complement of that. And now for the upper bound, we already use some standard graph embedding techniques. So let's try and greedily embed a tree into red. And let's say I have a vertex of degree. So now again, for the upper bound, we have red-blue coloring of this thing. Well, a complete graph on this many vertices, and we want to show that there's a red T or a blue Ks. So consider edge coloring. Consider an edge coloring of A, S minus 1, T minus 1 plus 1. So if I want to embed my tree greedily into red, maybe I ask, do I have a vertex of degree T minus 1 at least? And if the answer is yes, I can always embed my next vertex, except that I have to embed it from the, say, top or root. So I have my tree, and I pick a root, and I say that I'm going to embed it from the root in whatever ordering I want. The only thing that's important is that I don't somehow have, 3 neighbors of one vertex, and then I have to embed that vertex, and that, I'm making the job more difficult for myself. So I'm always requiring that whatever vertex I'm embedding, let's say this one, that it only has one neighbor that I've already embedded. Okay, so this is my tree. I'm embedding it from a root, And so I pick any vertex, and now it has, if it has at least t minus 1 neighbors, then I always have red neighbors. I always have a candidate for this next vertex. And that's, again, that's sharp because my tree might actually be a star. So then I genuinely may need t minus 1 red neighbors. So then I look at the next vertex. If it has at least t minus 1 red neighbors, I can embed its neighbor. And then I look at this one. If it has at least t minus 1 red neighbors, then I can embed all of its children, etc. So I keep going like that as long as all my red vertices have degree at least t minus 1. And we'll see that this property actually has important kind of graph theoretic implications and names, but for now we'll just use it. So case 1, suppose that G has a subgraph G prime G prime G prime in which every vertex has at least t minus 1 red neighbors. So not any neighbors, but red neighbors. In other words, I look at my red graph, and then I ask, is there a subgraph, red subgraph G prime with minimum degree at least t minus 1? And then I can embed greedily in red. Notice this, that specifically, if it has minimum degree t minus 1, then it certainly has at least t vertices. So that certainly makes sense. So then we embed t into G prime greedily. And we kind of got lucky because actually by this counterexample as well, in the opposite case, we exactly get to pick a green clique in a greedy fashion. So case 2. In every G prime subgraph of G, or rather in every induced subgraph, there is a vertex with red degree at most, so strictly smaller than t minus 1. And then I can greedily pick a green clique. Well, how? So I pick a vertex, this vertex with small red degree, and I'm going to put it into my clique, and I'm going to delete all these neighbors. And notice that I'm going to delete strictly less than t minus 1 vertices. So with that one move, I lose at most t minus 1 vertices, so I can repeat that s times. Why s times? Because after I've done it s minus 1 times, I still have at least one more vertex left, and then I'll be able to put it into my independent set. So basically, then inductively, let's say build or construct blue click as follows. So having picked V1 up to some Vi and removed at most I times t minus 1 vertices, let Vi plus 1 be a vertex of red degree at most t minus 1 in the remainder, so in the remaining graph. And then remove, so put, well, I defined this vertex to be Vi plus 1, so remove neighbors of Vi plus 1 at most red neighbors. Red neighbors, so at most t minus 2 of them. And this can be repeated. Repeat s times, and then V1 up to Vs is a blue Ks. Okay. And if you analyze this proof, you'll realize that it will produce exactly this as the kind of optimal counterexample for you. So basically, you look at this algorithm, and if it doesn't work, it means that you'll have in red, you need to have many vertices of degree t minus 2. And on the other hand, in this step, you'll have, so each vertex, let's say V1 is picked in here, it'll have precisely t minus 2 red neighbors, and by removing those, and those neighborhoods will be disjoint from all the other vertices I pick later, meaning that if I pick V1, I remove all its red neighbors, I've lost precisely t minus 1 vertices, and then I pick V2 in here, and there are no repetitions between the red neighborhoods, because if there were repetitions between the red neighborhoods, I would be able to gain on this proof, but this way the red neighborhoods are disjoint, so the proof kind of works optimally precisely for this kind of example. Okay, and this actually can be also generalized to a coloring graph, like vertex coloring algorithm. That's again the usual greedy coloring for graphs. So last time we saw that if we have a graph of maximum degree delta, then you can color its vertices in delta plus 1 colors with no monochromatic edges, so proper coloring. And this is actually a strengthening of that, so you don't need exactly degree delta plus 1. What you need is, once you successfully remove vertices, you always have a low degree vertex, and then you pick, so you can pick your ordering of the vertices that you're coloring. So specifically, if you're if you now look at, repeat this procedure in the red graph, what you can do is you can actually properly color the vertices of the red graph. I know it's confusing, using at most n over t minus 1 or something like that colors. And then one color is an independent set, and that gives you an independent set of size S. Yeah. Okay, so that is it about these trees. There's also a problem about tree versus tree. So there's a similar argument. It uses some of the stuff that we did now, telling you that the Ramsey number of t is big O of the number of vertices of t. So here, if you, instead of ks, you can also, of course, plug in a t, but you get a quadratic bound. And this says that actually, if you want a red tree versus blue tree, then you can also have a linear bound. And this constant is something reasonable, like 4. But what constant exactly it should be, it depends on the tree, so that's why we did these examples. So, for instance, for paths and stars, you can exactly determine it, but you know, for general trees, it's harder to tell what exactly this is. And actually, it's related to a famous extremal problem for trees due to Erdős and Sors. So, Erdős and Sors asked what's the maximum number of edges you can have in an n-vertex graph not containing a specific tree T. And now I don't have the specific conjecture here, but it's something like 2Tn. So in an n-vertex graph, if you have at least 2 times t times n edges, then you get every n-vertex tree. No? Am I? Okay, I'll look up that conjecture later. But anyway, if you then apply that conjecture to the majority color, you get a bound. You get an improvement because this really, you get an improvement on the Ramsey number of trees. Because really, hint for this problem, the hint for this for this Ramsey number is to just look at the majority color, so it doesn't really depend on the coloring. Okay, so then so this motivates the question: for which graphs are the corresponding Ramsey numbers linear in n, where n is the number of vertices of the graph. So, and here I'm taking your guesses. So, you know, just to see your intuition. It really doesn't have to be correct. So, I somehow seem to have old lecture notes, sorry. So, general question, for which age is the Ramsey number of age, so the red age or blue age, linear in the number of vertices of age. So, I'm interested in some necessary and sufficient conditions for this, if you can come up with them. So what do you think? So we've seen that this definitely holds for, well, you can prove that it holds for trees, and we know it's true for, it's not true for cliques, and what about in between? So I guess so far the only kind of graph parameters that we know are the number of edges and maybe the maximum degree, or actually this kind of parameter is relevant, the so-called degeneracy that also played a role in Bruno's thesis. So yeah, the only thing and you know, you can also think of planarity, similar, more exotic properties. So you can ask, okay, is it true for age with a bounded maximum degree? So let's say this vertex now again, it's important to imagine that the number of vertices of this graph is n, it goes to infinity, but we want to put a bound on, say, the maximum degree or the average degree. And that's the kind of questions are we asking. So is it true when the max degree is it, well, some constant, but let's put a specific constant here. Is it true? Is it sufficient? And is it true when the average degree is bounded? So let's say the number of edges is at most, say, 1000 n. So notice that trees satisfy this. Actually, not all trees satisfy this, but say, you know, paths do. So, yeah. Any guesses about these? Yeah. Okay, so for maximum degree it's true, and we're going to prove it, but much later in the course because we need the Semiramis regularity lemma. For this one, it's not true. So maybe a question for you is why this is not true, and I mean it's an easy example, so it just shows that this is maybe too naive, I guess. So yeah, it's not hard to come up with an example. So to challenge for you, find the graph age with at most 1000 n edges, which has a much larger, say, super polynomial Ramsey number. And maybe also another problem that's interesting to do, especially if you haven't done the standard Ramsey number lower bound, it shows that the latter condition is necessary but not sufficient. So problem 3.3 says that if age is a graph, an n-vertex graph, but it actually doesn't matter here, graph with average degree d, then the Ramsey number of age is at least 2 to the d minus 1 over 2. I think that's what it says. So that's just an adaptation of the usual Ramsey number lower bound. So if you understand that, you don't have to do it. If you haven't done it, I recommend it as a problem. But basically what it says is that this is necessary or almost necessary to have a linear Ramsey number, but it's certainly not sufficient. So does anyone have an idea why it's not sufficient? So what can go wrong in this graph with a small number of edges is that all these edges can be concentrated on a very small number of vertices. So what would be an example of such a graph?
Log n with additional vertices.
Yes, but you don't have to, it's not even log n, it's just square root n. Right. Yeah. And if you really, if you want it to be connected, if you think that's a cheat, so, okay, so 2 is not sufficient. So if we have a clique on square root n vertices and a whole bunch of isolated vertices, then, you know, that has a number that's exponential in square root n, so it doesn't help. And if you think this is a cheat, even though formally it's okay, you can just put a path here and, you know, same thing. Okay, so that doesn't work. And now, and actually a challenge, okay, so this gives a lower bound of order 2 to the square root n. So one can also ask a question, can it be exponential in n? Like truly exponential, not 2 to the square root n? And the answer to that is no, but it's some further research that I'm not going to mention. Okay, so this thing, we're going to prove. It's a theorem of Hvatal, Trotter, Semeredi, and someone else, Redl. Hvatal, Redl, Semeredi, and Trotter from '83, and it's one of the classical applications of Semeredi's regularity lemma. And for this one, we can have a refinement. So actually, that was a conjecture of Erdős and Bohr, which is very natural, and they conjectured that it holds for all D-degenerate graphs, which are exactly the kind of graphs that we have just looked at. So the conjecture of Erdős and Bohr, which is now a theorem of Chung-Bam Lee, this was around 2014. If G is a D-degenerate, and I'll define that, n vertex graph, then the Ramsey number of G is at most some constant, but this constant may depend on D, and the dependence is horrible, times n. So that's Chung-Bam Lee's beautiful theorem. And what does this degenerate mean? The degenerate mean? Well, it's precisely what we had in the problem before. It means that every subgraph has a vertex with degree at most D, and it prevents this kind of silly example. So D degenerate. There are two equivalent ways to define it. One is that every subgraph has a vertex of degree at most D, and another one is in terms of orderings. So this is equivalent to saying that I can order my vertices in a way that everyone has at most D backward neighbors, because I can take vertex of degree at most D in the original graph, then I can remove it, take the next vertex, remove that one, etc. So each vertex in that ordering will have at least D backward neighbors, and that kind of property is very useful for embedding and coloring. And again, it was also present in Bruno's PhD thesis. Okay, so that's a theorem of Chung-Bam Lee. And of course, if you have maximum degree D, then you're also D degenerate. It goes without saying. And yeah, one important example, actually there's two examples. So this covers trees, because trees are one degenerate. In other words, every tree has a leaf. So the leaves will give you the vertices of degree at most 1. And actually planar graphs, or any graphs that you can embed in a fixed surface, are also D degenerate with some constant D. So planar graphs are 5 degenerate because you can always find a vertex of degree at most 5 and remove it. And that's actually how you can prove that you can 6-color vertices of a planar graph properly. Okay, and then so this was a very short chapter because most of the work is the proof of this, which we'll have to do much later. But then we'll move on to edge Ramsey numbers. So the follow-up question might be, or in Croatian, I've translated it as Ramsejevi bridni brojevi. So now we're trying to minimize the number of edges in a graph such that in a graph which contains age in any red and blue coloring. So maybe I'm getting a bit ahead of myself because I realize that that's now you have two graphs in play, so it gets a bit more complicated. So basically, the intuition is, the question is, here I found a complete graph for trees, say. I found a complete graph on n vertices, or t vertices, where t is the size of the tree, such that any red-blue coloring of this graph contains a copy of t. But notice that this is still somehow not optimal because the number of edges in this complete graph is quadratic in t. So now we want even more. We want a large graph that has a number of edges that's linear in t and still has this kind of Ramsey property. So basically, we define this relation, G arrows age, or G is Ramsey for age. If every red-blue coloring of edges of G contains a monochromatic, so red or blue, age copy. So, for instance, we proved that K6 is Ramsey for K3. More generally, we proved that K4 to the T is Ramsey for KT. So everything so far we did was for complete graphs. We also proved that well, we didn't prove, but you can prove that K4T is Ramsey for any T vertex tree. Okay, so now again we're coloring the edges of this graph and we're asking for a monochromatic copy of the other graph. And the question now, the challenge is to find a graph with as few edges as possible. So this is a question that you can already ask for cliques, and it's interesting. So already for this problem, I can ask, okay, so this is exponential and this has to be exponential, but maybe I can find some huge graph on, or some much larger graph, but with a smaller number of edges. So a graph that's larger but sparser, that still has this property for KT. And it turns out that this is impossible. So that's another problem that I want to finish with that you can think about for next time. And it says that if G is Ramsey for the clique KT, then the number of edges of G is at least what you get in the optimal Ramsey, in the optimal clique for T. So again, Ramsey number of KT is the minimum number of vertices you need in a Kn to be Ramsey for KT. This is the number of edges you need in such a Kn. And this problem says that you can't do better by trying to take some other graph G. Okay. So that would be it. Well, maybe questions first. Okay. Then that'll be it for today. So next week we don't have a lecture. Good luck to everyone at the national competition. And then we return again in 2 weeks' time. Thanks.